One of the most groundbreaking innovations in artillery during World War II was the development of the proximity fuse. Before this invention, artillery shells relied on either impact or timed fuses, which were often inaccurate. Timed fuses required careful calculations to detonate at the right altitude. But even small errors in timing would make shells ineffective. The proximity fuse solved this problem by using miniature radio transmitters and receivers inside the shell. When the fuse detected it was within a certain distance of a target, like an aircraft, it triggered detonation automatically. This significantly increased the effectiveness of anti-aircraft fire. Instead of needing a direct hit, shells could now explode close enough to damage or destroy enemy aircraft. This innovation played a vital role in defending Allied fleets from Japanese kamikaze attacks and in protecting cities from German air raids. Beyond air defense, the fuse was also adapted for ground combat, creating devastating airbursts over enemy infantry positions. By increasing accuracy, lethality, and versatility, the proximity fuse transformed artillery into a more precise and deadly battlefield tool, cementing its role as one of the most significant wartime innovations of the 20th century. The proximity fuse had a revolutionary impact on the way artillery was perceived in military strategy. Prior to its introduction, commanders often had to rely on overwhelming volumes of fire to achieve results. Aimed fire against moving aircraft or dispersed infantry was notoriously inefficient. With proximity fuses, artillery became a weapon of efficiency rather than just brute force. American forces were the first to deploy this technology extensively, thanks to close collaboration between military engineers and civilian scientists, including contributions from the Massachusetts Institute of Technology and British research teams. When used in the Battle of the Bulge in December 1944, proximity fused shells wreaked havoc on advancing German troops, causing widespread panic and disorganization. Soldiers described the shells as if the air itself exploded. By ensuring that rounds detonated at optimal distances, they multiplied the effectiveness of each shell fired. This not only conserved ammunition, but also allowed artillery units to deliver far greater psychological shock. Proximity fuses thus shifted artillery doctrine toward precision fire, reshaping how modern armies approached battlefield suppression and area denial. Their legacy continues today in guided munitions and advanced sensor-based weaponry. Another major innovation of World War II was the introduction of self-propelled artillery. Traditional towed artillery had dominated battlefields for centuries, but it came with serious limitations. Once a towed gun was set up, it required significant time and manpower to reposition. This meant that artillery could not easily keep pace with fast-moving armored units or retreat quickly, if threatened by enemy counterattacks. Self-propelled artillery solved these problems by mounting heavy guns on armored, motorized chassis. Vehicles like the German Wespe and Hummel, the American M7 Priest, and the Soviet Su-76 provided mobility, protection, and firepower in one package. They allowed artillery to move with tank formations, offering continuous fire support without delays. This mobility proved crucial in modern mechanized warfare, where speed and flexibility determine success. Self-propelled artillery also gave crews better survivability, since the vehicles were armored and could withstand small arms fire and shrapnel. By combining mobility and firepower, self-propelled artillery changed the dynamics of land warfare, bridging the gap between tanks and traditional artillery while setting the stage for post-war war armoured doctrines. The development of self-propelled artillery also reflected the broader mechanization of World War II. Blitzkrieg tactics pioneered by Nazi Germany emphasized rapid advances and deep penetrations, supported by close cooperation between armor, infantry, and artillery. Towed artillery could not effectively support these rapid maneuvers, often lagging far behind or becoming vulnerable to air strikes and counterattacks. In contrast, self-propelled guns could advance with tank formations and reposition within minutes, delivering sustained firepower wherever it was most needed. The US Army's M7 Priest, for example, became a workhorse in both Europe and the Pacific. It carried a 150 mm howitzer and could provide mobile fire support for infantry and armored divisions alike. Meanwhile, the Soviet Red Army mass produced vehicles like the Su-76 to accompany its vast tank armies in their drive toward Berlin. These innovations not only provided better battlefield flexibility, but also foreshadowed the future of artillery in mechanized armies. Today, nearly all modern artillery is self-propelled, and its lineage can be traced directly back to World War II's groundbreaking experiments in mobility and firepower integration. Rocket artillery represented another dramatic leap in technology during World War II. Unlike traditional artillery shells, rockets were cheaper, faster to produce, and capable of being fired in devastating barrages. The most famous example was the German Nebelwerfer, which could unleash a salvo of rockets that caused not only physical destruction, but also immense psychological terror. Its shrieking sound earned it the nickname "Screaming Mimirs" among Allied troops. While the Nebelwerfer was not as accurate as conventional artillery, its sheer destructive power over a wide area made it invaluable for saturating enemy defenses before an attack. The Soviets, however, took rocket artillery to another level with the Katyusha multiple rocket launcher, also known as Stalin's organ, mounted on trucks. Katyushas were highly mobile and capable of launching massive rocket salvos that could devastate German positions within seconds. These rocket systems allowed the Red Army to deliver concentrated firepower on a scale that was previously unimaginable, giving them a crucial edge during major offensives. Although rockets lacked the precision of traditional guns, their speed, volume, and psychological impact redefined how massed firepower could be delivered on the battlefield. The success of rocket artillery in World War II marked the beginning of a new era in long-range firepower. Unlike towed or self-propelled guns, rocket launchers could be rapidly reloaded and redeployed, making them ideal for mobile warfare. The Katyusha, in particular, played a pivotal role in Soviet deep battle doctrine, which emphasized overwhelming force applied at multiple points along the front. By saturating enemy positions with rockets, Soviet commanders could disrupt communications, destroy fortifications, and demoralize defenders before infantry and tanks advanced. German soldiers often described the terrifying effect of a Katyusha barrage as worse than conventional shelling because of the unpredictability and intensity of the explosions. Meanwhile, American forces experimented with rocket artillery like the Calliope, mounted on Sherman tanks, which provided devastating firepower in support of ground assaults. These wartime rocket systems laid the foundation for post-war developments in missile technology, ultimately influencing everything from modern multiple launch rocket systems, SAMRS, to intercontinental ballistic missiles. Thus, rocket artillery was not just a weapon of the moment, but also a stepping stone toward the future of warfare. while weapons themselves were critical. Innovations in fire control during World War II were equally transformative for artillery effectiveness. Before the war, artillery targeting relied heavily on manual calculations, rudimentary range tables, and forward observers who often struggled to relay accurate information quickly. World War II introduced more advanced fire direction centers, mechanical computing devices, and improved communication systems that allowed artillery units to coordinate with unprecedented accuracy. The British, for example, developed the prediction by computation method, which enabled guns to fire accurately without registering shots beforehand. This meant artillery could deliver devastating surprise bombardments without warning the enemy. The U.S. Army also advanced its fire direction systems, using early analog computers and improved radio networks to coordinate massed fire from multiple batteries simultaneously. These improvements allowed armies to unleash time-on-target barrages, where dozens of shells from different guns landed on an enemy position at the same moment. The shock effect of such barrages was enormous, often overwhelming defenders before they had a chance to react. This combination of precision, coordination, and surprise gave Allied artillery a decisive edge on the battlefield. The improvement of fire control systems during World War II not only made artillery more accurate, but also increased its integration with other branches of the military. Artillery was no longer an isolated force delivering random bombardments. It became a carefully coordinated tool of combined arms warfare. Forward air controllers, reconnaissance aircraft, and ground observers could now transmit real-time information to fire direction centers, dramatically reducing the time between spotting a target and firing on it. This responsiveness meant that artillery could neutralize enemy armor, suppress counterattacks, or support infantry advances with minimal delay. For example, during the North African campaign, British and American forces perfected the use of artillery concentrations to break up German armored thrusts, often stopping them cold. On the Eastern Front, Soviet artillery coordination allowed for devastating pre-assault barrages that shattered German defenses ahead of massive offensives. These advances in fire control foreshadowed the digitized targeting systems of today, where satellites, drones, and GPS technology allow artillery to strike with even greater precision. In this way, World War II fire control systems represented a turning point in the science of battlefield coordination. Among the more dramatic innovations of World War II was the development of heavy long-range artillery and superguns. Both Axis and Allied powers invested heavily in massive guns, capable of bombarding targets from incredible distances. Germany's most famous example was the 800 WW2 Schwerer Gustav, the largest caliber rifled weapon ever used in combat. This colossal gun could fire shells weighing nearly 7 tons at ranges over 30 miles, designed to demolish heavily fortified positions like those of the Maginot Line. Although the Schwerer Gustav was logistically impractical, it required thousands of men and weeks to set up. It symbolized the extremes of artillery innovation during the war. Other long-range weapons, like the German V3 cannon, experimented with new propulsion methods to extend ranges beyond conventional limits. On the Allied side, heavy artillery such as railway guns and naval bombardment cannons provided critical firepower for sieges and amphibious assaults. While not as mobile or flexible as other innovations, these massive guns demonstrated the ongoing quest for range and destructive power, influencing Cold War Era experiments with large caliber artillery and rocket-assisted projectiles. The fascination with heavy artillery during World War II also reflected the symbolic power of superweapons. Hitler in particular placed great faith in wonder weapons that he believed could turn the tide of the war. While the Schwerer Gustav and its counterpart, Dora, were engineering marvels, they had limited strategic impact due to their logistical challenges. Nonetheless, they highlighted the lengths to which nations would go to achieve artillery dominance. Long-range guns also served practical purposes. Coastal artillery, such as German batteries along the Atlantic Wall, used enormous guns to defend against Allied invasion fleets. Similarly, the Allies deployed powerful naval artillery during the D-Day landings to pound German fortifications before troops went ashore. These heavy weapons showed that artillery still played a vital role in both offense and defense, even in the age of air power and mechanized warfare. Though the age of superguns largely ended with World War II, the ambition behind them paved the way for later experiments with rocket-based long-range bombardment and even space-launch technology. They remain enduring symbols of the era's obsession with military scale and firepower. Beyond their immediate battlefield effectiveness, proximity fuses had long-term implications for how armies designed and deployed artillery. They transformed artillery from an area saturation weapon into a precision system capable of efficiently neutralizing moving and airborne threats. This also reduced the logistical burden on armies, since fewer shells were needed to achieve results. In naval warfare, proximity fused anti-aircraft shells proved invaluable during the Pacific Campaign. The U.S. Navy, plagued by kamikaze attacks, found that ships equipped with proximity fuses had dramatically improved survival rates. A single shell exploding near an incoming plane often destroyed or disabled it before impact. On land, proximity fuses made defensive artillery fire vastly more lethal against massed infantry or tank assaults. Their introduction in the Battle of the Bulge shocked German soldiers, many of whom had never experienced such devastating air bursts. In psychological terms, this created fear and hesitation in enemy ranks, undermining morale. The success of proximity fuses also encouraged post-war investment in electronic warfare, as they were among the first examples of miniaturized electronics used in combat. Thus, proximity fuses represented not just a wartime innovation, but also a foundation for the future of precision-guided weaponry. Self-propelled artillery also demonstrated how mobility and protection could transform logistics and strategy. Traditional towed artillery units required large teams of horses or trucks, making them vulnerable to air attacks, mud, and road congestion. Self-propelled systems, however, were designed to move under their own power, freeing up supply lines and simplifying deployment. They could traverse rough terrain alongside tanks, ensuring that fire support was never far behind advancing units. In the brutal Eastern Front campaigns, this mobility allowed the Soviets to maintain constant pressure on German forces during rapid advances. The M7 Priest in North Africa gave Allied units the ability to conduct shoot and scoot tactics, firing and then quickly repositioning before the enemy could counterattack. This survivability feature was crucial in the age of aerial reconnaissance and counter-battery fire. Post-war, the lessons learned from self-propelled artillery influenced the design of modern armored units, where artillery is expected to operate as seamlessly as tanks and infantry. It established a doctrine where artillery was no longer static but part of a dynamic, integrated force, paving the way for the highly mobile mechanized artillery systems of today. Rocket artillery also had a profound psychological impact that was disproportionate to its physical destruction. When German Nebelwerfers fired, their eerie screeching noise often caused panic among Allied troops before the rockets even landed. Similarly, Soviet Katyusha barrages stunned German defenders, shaking morale and disrupting command structures. While their accuracy was poor compared to traditional guns, their ability to saturate large areas in seconds made them ideal for shock tactics. Entire sectors of the front could be softened up rapidly, creating opportunities for armoured breakthroughs. The mobility of truck-mounted Katyushas made them difficult to counter, as they could fire and relocate within minutes, avoiding counter-battery fire. This tactic became so effective that the Germans prioritized hunting Katyusha units whenever possible. Despite their shortcomings, rockets were cheap and easy to mass produce, allowing even resource-strained nations to deploy them in large numbers. By the war's end, the world had recognized the enormous potential of rocket-based weapons. The post-war development of multiple launch rocket systems, MMLRS, and tactical missiles was directly inspired by the wartime effectiveness of Nebelwerfers and Katyushas, making rocket artillery one of the most influential innovations of the conflict. The improvements in fire control during World War II also demonstrated the growing importance of mathematics and science in warfare. Before the war, artillery officers relied heavily on field experience and simple range tables. By 1945, armies were employing mechanical calculators, advanced ballistics tables, and integrated communication systems. This scientific approach allowed commanders to plan complex fire missions involving dozens of batteries, spread over miles of terrain. Time on target. Tactics perfected by the US Army were particularly devastating. By carefully calculating firing times, shells from widely dispersed guns could land simultaneously, overwhelming enemy positions without warning. This level of coordination was only possible because of improved fire direction centers and faster communication networks. It also marked a cultural shift. Artillery became a science as much as an art. The ability to predict trajectories with precision foreshadowed the computerization of warfare in the Cold War. Today's digital fire, control computers, GPS targeting, and networked artillery systems all trace their roots back to the innovations of World War II. The war proved that superior organization and coordination could multiply the effectiveness of firepower, often more than raw weapon size or shell count. While heavy long-range artillery and superguns were impressive engineering feats, they also highlighted the limitations of oversized weapons in modern warfare. The Schwerer Gustav, despite its massive shells and destructive capability, was so unwieldy that it was almost impractical. Transporting it required dozens of railway cars, thousands of men, and weeks of preparation. In a war defined by mobility and speed, such a weapon was more of a prestige project than a practical battlefield tool. Similar issues plagued other superweapons like the V3 cannon. These weapons consumed enormous resources that might have been better spent on more mobile and versatile systems. Yet, their development reflected the desperation of nations like Germany, which sought technological shortcuts to overcome strategic disadvantages. On the Allied side, heavy artillery proved more useful in naval and coastal defense roles where mobility was less critical. Naval guns, for example, played decisive roles in bombardments during the Normandy invasion. Ultimately, superguns taught militaries that size alone did not guarantee effectiveness. Post-war militaries shifted focus toward versatility, precision and mobility, leaving giant artillery pieces as relics of a bygone era. Another lasting impact of these World War II artillery innovations was their integration into combined arms warfare. The war demonstrated that no branch of the military could succeed in isolation. Artillery, infantry, armor, and air power had to cooperate closely. Proximity fuses made artillery more effective at protecting infantry from air threats, while self-propelled guns ensured tanks always had supporting firepower. Rocket artillery disrupted enemy defenses before assaults, and improved fire control allowed for seamless coordination between different units. This synergy was particularly visible in Soviet operations, where massive artillery barrages, followed by waves of tanks and infantry, crushed German defensive lines. The Western Allies also perfected combined arms at Normandy, where naval bombardments, artillery fire, and airstrikes all worked together to support landings. The success of combined arms operations showed that artillery was not merely a supporting element, but a central pillar of modern warfare. Post-war military doctrine institutionalized this approach, ensuring that artillery remained integrated into every aspect of combat planning. Without the artillery innovations of World War II, modern combined arms strategy would look very different today. Artillery has always had a psychological dimension, but the innovations of World War II amplified this effect. Proximity fused shells created sudden, devastating airbursts that terrified soldiers caught in the open. Rocket artillery produced unforgettable sights and sounds that shook morale, even when physical casualties were limited. The knowledge that enemy artillery could strike with unprecedented speed, accuracy, and destructiveness weighed heavily on soldiers' minds. Accounts from the Battle of the Bulge reveal German troops describing the new American proximity fused shells as inhuman, spreading panic across entire units. Similarly, Allied troops in Italy dreaded the wailing of German Nebelwerfers, which earned a reputation out of proportion to their actual lethality. This psychological warfare element magnified the effectiveness of artillery, as demoralized troops often fought less effectively or abandoned positions prematurely. Military leaders recognized this and increasingly used artillery not just to kill but also to intimidate and suppress. This dual role, physical destruction and psychological dominance, became a cornerstone of modern artillery doctrine, a lesson carried forward from the terrifying battlefields of World War II. The artillery innovations of World War II directly shaped the technologies of the Cold War and beyond. Proximity fuses introduced the concept of smart munitions, leading to the guided missiles and precision bombs of later decades. Self-propelled artillery became standard, with vehicles like the American M109 and Soviet 2S1 carrying forward the concept of mobile, armored firepower. Rocket artillery evolved into advanced multiple launch rocket systems, capable of delivering both conventional and nuclear warheads. Fire control systems, which had relied on mechanical calculators during the war, became computerized in the 1950s and eventually digitized in the late 20th century. Even the dream of long-range superweapons lived on. Not in giant cannons, but in intercontinental ballistic missiles, which applied the same principles of long-range bombardment through rockets. Thus, World War II artillery innovations were not just battlefield tools, but stepping stones toward the modern military technologies that dominate today's conflicts. They bridged the gap between traditional gunpowder artillery and the high-tech missile systems that define 21st century warfare. Artillery innovations also forced militaries to rethink their strategies and logistics. Proximity fuses allowed armies to achieve more with fewer shells, reducing ammunition supply burdens. Self-propelled artillery simplified deployment and repositioning, easing logistical headaches on fast-moving fronts. Rocket artillery, though less precise, could deliver immense firepower with relatively lightweight and easy to produce rockets, relieving industrial strain compared to heavy artillery production. Fire control improvements reduced waste, ensuring every shell had a higher chance of hitting its target. Even superguns, though largely impractical, highlighted the need for efficient supply and deployment systems. Collectively, these innovations demonstrated that logistics was as important as firepower. The ability to supply, move, and coordinate artillery became central to military planning. Post-war militaries absorbed these lessons, emphasizing mobility, efficiency, and precision in artillery design. The logistical challenges of World War II created a generation of officers who understood that wars are won not only by firepower, but by how effectively that firepower is delivered and sustained. By the end of World War II, artillery was no longer the same weapon it had been in 1939. Proximity fuses revolutionized accuracy and effectiveness. Self-propelled artillery gave unprecedented mobility. Rocket artillery introduced new levels of shock and massed firepower. Improved fire control systems, enhanced coordination and precision, and superguns demonstrated both the potential and limits of scale. Together, these innovations reshaped the role of artillery from a blunt, area, saturation tool into a flexible, precise, and integrated element of modern warfare. They also provided the foundation for post-war advances in missile technology, guided munitions, and computerized fire systems. The Second World War proved that innovation in artillery was not just about building bigger guns, but about integrating science, technology, and strategy to multiply effectiveness. Even today, modern artillery systems, from GPS-guided shells to mobile rocket launchers, owe their existence to breakthroughs made during those 6 years of global conflict. Thus, World War II stands as the pivotal moment when artillery truly entered the modern age, changing the nature of warfare forever.